this video, we will learn about optimum problem. So, solving optimum problem is basically an application of second derivative test and first derivative test. We can call this as a application because most of the time the problem would be for our real life application situation where we have to find the maximum of a volume, maximum of an area, maximum radius, maximum height, and so on. So basically, we will use the concept of first derivative test and second derivative test. Below are the steps for solving optimum problem. Bear in mind this is basically just a guideline because the situation would be very based on the problem given. So now let's do some example. So example 6, we have a rectangular region is formed by 16 cm string. Find the length x squared and the width of y of the region if the area of a region is to be maximum. Hence, find the maximum area of the rectangular region. So based on the information given in the question, we will know that now we have a rectangular shape with the length of x squared and our width would be y. From here, our next information is we have to find the maximum area. So formula for area, as we know, would be length times width, and in this case our equation would be A, stand for area, would be equal to x squared times y, and I denoted this as my first equation. Next, we figure something out based on the information given from the first sentence itself. This region is formed by 16 cm string, means that they use the concept of perimeter. So from the information, we can deduce the equation of 2x squared plus 2y equal to 16. 2x squared plus 2y is basically the perimeter of our rectangular region. If I simplify this out, we will get x squared plus y equal to 8, and I denoted this as our second equation. Why we have to find the two equation? Because basically in order to find the maximum value, we have to differentiate our area equation. But at this point, we cannot differentiate this because we have two different variables here, which is x and y. In order to differentiate this, we have to manipulate this equation so that we're gonna have only one value. Only one variable. So from our second equation, I rearrange this by making y as my main subject. So we will get 8 minus x squared, and I will substitute this into our first equation. That's how we get A would be equal to x squared times with 8 minus x squared, resulting 8x squared minus x to the power of 4. Now, we already have an area equation with only one variable of x. After that, we can differentiate this. So, derivative of a with respect to x would be dA over dx. Differentiate 8x squared, you will get 16x, and differentiate x to the power of 4, we will get 4x cubed. After that, in order to find the value of x, we have to equate this to 0. So, if our dA over dx equal to 0, means that 16x minus 4x cubed equal to 0. I can factorize 4x outside, so we will get 4x times with 4 minus x squared equal to 0. From here, we will get three values of x, which are x equal to 0, x equal to negative 2, and x equal to 2. Based on the situation, since x is basically length, we have to reject some of the values. In this case, we have to reject x equal to 0 and x equal to -2 because these numbers are impossible to be as our dimension. Now we only left with one value, which is x equal to 2. But then we still not sure whether x equal to 2 will give a maximum result. So now we have to check whether x equal to 2 will provide a maximum area for our rectangular region. In order to do so, we have to perform second derivative test. So from our first derivative equation dA over dx equal to 16x minus 4x cubed, now we have to differentiate this equation once more. So we will get 2d squared a over dx squared equal to 16 minus 12x squared. After that, in order to check whether x equal to 2 provide a maximum result, you just have to substitute x into this equation. So if I substitute x equal to 2 into our second derivative equation, we will get a negative result. So we have a sad face result. Means that this is a maximum value. So from here, we can conclude that x maximum would be 2 cm. So following the question, they ask for x squared. So we will have x squared maximum would be equal to 4. Y maximum would be also equal to 4. Means that our area that is maximum would be equal to 16 cm squared. Now let's do another example. So example 7, we have a cylindrical container has one end that open and the other end is closed. Means our cylinder is open at the top. It has a circular base of radius r. Given that the total surface area is 300 pi centimeter squared. So part A, we have to show that the volume of the container is V equal to 150 pi r minus pi r cube divided by 2 centimeter cube. And part B, we have to find the maximum value of V. Means we have to find the maximum volume. So we do part A first. So based on the situation, we have a cylinder. And as we know, the general formula for cylinder would be V equal to pi r squared h. But based on the question, we can see that now we have a different equation of V, where our V is now fully in the term of R. We don't have H in our volume equation. Means now we have to manipulate this equation so that we can show what they ask for. So in order to do so, you just use any information given in the question. So as we highlight before, the only information they provide is the surface area. So our surface area equation I denoted as S equal to pi r squared. We only have one circle here because our cylinder is open at the top, plus 2 pi r h. This is the general formula of surface area. Next, the info gives that the surface area is 300 pi. So I can substitute this and get a equation pi r squared plus 2 pi r h is basically 300 pi. So using this equation, since we want to eliminate h on the volume equation, we can make h as our main subject. Rearrange this. We will get basically h is 300 minus r squared divided by 2r. After that, we just substitute h into our volume equation. So we will get pi r squared and h now will be 300 minus r squared divided by 2r. But at this point, this is still not the equation that the question asks for. Means that we have to do simplified version. So we can separate the fraction, and after that open up the bracket, and after you simplify, we will get our V is basically equal to 150 pi r minus pi I cube over 2, and this is what they asked for. Settle part A. Now, moving on to part B, we have to find the maximum value of V, means the maximum volume. In order to find maximum volume, we have to find maximum value of R, in this case our radius first. So, our first step is basically by differentiate our volume equation with respect to R. So, since we have the volume equation in the term of R, differentiate this, we will get dV over dR equal to derivative of 150 pi R. We just differentiate this as usual, so you will get 150 pi. Derivative of pi r cube, differentiate r cube, we get 3r squared. So that's how we get 3 pi r squared over 2. And this is basically our dV over dr. So to obtain value of r, we have to equate this to 0. So if I equate this to 0, we will get value of r is either positive 10 or negative 10. But finally, since r is basically a radius, we have to choose a positive value. So our r in this case would be 10. We still not done yet because we not sure whether r equal to 10 is basically a maximum r. So in order to confirm this, we have to perform second derivative test. In order to find the second derivative equation, basically we just have to differentiate our first derivative equation once more, and we will get our d squared v over dr squared will be in this case equal to negative 3 pi r. I repeat, you just have to basically differentiate your first derivative equation. Now, in order to check whether r equal to 10 is the maximum radius, now we just have to substitute r into our second derivative equation. By doing so, from here we know that this will give a negative result. Since we get a sad result, we can now ensure that this is basically a maximum value. So we can conclude now that R maximum in this case is basically 10 centimeter. Since we already have a maximum value of R, in order to find the maximum value of volume, we just have to substitute R equal to 10 into our V equation. So by doing so, finally we will get a maximum volume here is 1000 pi centimeter cube.